Okay, so in the previous lecture we talked about how to generate a mesh for your domain for very complex geometry or multi-physics systems, and how to define an interpolant patch or a finite element and its values on one of the patches there. So now what we're going to do is talk about how do we now start talking about solving PDEs on that mesh using those finite elements. Okay? So the first thing we're going to do is revisit this picture. So this picture here is to talk about, I'm going to approximate my PDE in patches like this, where every patch is in fact a little simplex element. We're going to start with simplex elements because they're the simplest thing to work with, and I'll also tell you a little bit more about this as we go along. So that's the idea though. Approximate the PDE there, but of course now this solution itself obeys a PDE. So these points on the solution actually must be constrained by being a solution to a partial differential equation that we're going to impose in this system. Right? They just can't be anywhere they want. We have to say, solve this, but with the constraints that the solution points, these points that we have, are in fact solutions to some PDE or approximate a PDE with some accuracy. So let's talk about the PDE we want to consider here in this example. I'm going to start off with an elliptic PDE. In other words, there's no explicit time dependence, there's no time marching, it's just a steady state solution. Now if you recall, when I first started talking about discretization, especially when we started talking about it in the context of finite differences, I also started off with a time independent problem, which was solving for the stream function in terms of the vorticity, which is the Poisson equation. And there what we just wanted to consider is just how do you discretize, set up the problem for solution, and that ended up in AX equal to B. And similarly, this time dependent problem is going to end up in an AX equal to B. Okay? And mostly what I want to show you is how this architecture is going to work. So what you're looking at here is this has two derivatives in X, two derivatives in Y, but it's with a non-constant coefficient here in front of that second derivative, so P and Q, and there's a generic R function with some forcing F. Okay? And what we're going to do is specify this on some complex boundary. So on one portion of the boundary, we specify what U is. On the second portion of the boundary, we specify, a much more sophisticated, given a normal direction on the boundary, and so we specify something quite a bit more complicated. Okay, and so let me show you a picture of this. This is what maybe it looks like. In a lot of finite element textbooks, you'll see a kidney-shaped bean like this and say, this is my domain. And of course, as soon as you plot this domain, you understand right away that this is very hard for finite differences or spectral methods to do. And so right away, even with a simple kidney shape, it sort of takes you outside of doing finite differences and spectral methods, and it puts you in a frame of reference of finite elements. And so on part of the domain, this S1, which is over here, we just specified the solution by here we go back here, by this G of xy. But on the second part of the boundary, we're going to look at the normal direction. We're going to expect, we're going to impose some kind of boundary condition that's more complex. Sorry, come back here, which is related to the normal across that derivative, the normal and the tangent, plus the solution itself. So this is kind of trying to illustrate that you can do very complex boundary conditions in solving these finite element representations. So that's your boundary, that's your domain. How do we get a solution for this? Now what we've talked about is the first step is to generate a mesh. So the mesh is going to be, let's say if we use simplex method, we get to pick a method to use. We'd love to use simplex, but there is kind of an issue with this. So if I use a simplex method, it's based on a plane. Complex on quadratics, and then multiplex based upon with this extra nonlinear term there. So the problem with using a simplex method here, in this problem, it has two derivatives. If you take two derivatives of this, it's just zero. In other words, the second derivative conveys no information at all to you. And so a simplex method is not appropriate to use if you're going to have two derivatives. Okay? So this is a huge issue. But I would really like to work with simplex methods because they're so simple, right? Parameterized by not many terms. So is there any way I could still do this problem and work with the simplex method? And the answer is yes. And the way what we're going to do is we're going to take the PDE as formulated here, which is a second order PDE, because it's got the highest derivative is second order in x and y, and we're going to turn this into its weak form. So we're going to use what's called the variational principle and turn this into the weak form, and in the weak form the highest derivative is one derivative. So if I take one derivative of my simplex, I retain information. So this is an important step to take, because what it does for you is it allows you to use simplex methods all the way up into second order PDEs. Okay? And it then allows you a much simpler representation and a much simpler solution solve. So the way we do this, write it in weak form, is we consider the following calculus variation arguments. We're going to talk about having here in the weak form defining this function I, which is the integral of some function f over the volume plus the boundary conditions parameterized g. So f and g, this is the boundary conditions because we're only integrating over the surface. Here we're integrating over the volume. Okay? And so what we're going to think about is taking derivatives of this function f, for instance. This is in the interior, so this is where the PDE would work. This interior in the volume, this is for the boundary conditions, but in the interior, what we're going to think about is this function f is if I take variational derivatives of this, so the variational derivative is a generalization of the derivative concept itself through calculus of variations, but that derivative is defined by the following. So you take the partial derivative of f with respect to phi of x, then x derivative, take the partial derivative of y with respect to phi of y, and y derivative, and so forth, minus dphi df dphi. And that's equal to 0. So this is essentially like minimizing this solution by taking this variational derivative of calculus of variations. Okay? So this is called the weak form. And this is the weak form of the PDE here. That's the weak form of the boundary conditions. And here's what the variations tell us. So let's go compute this. In other words, what we want to do is we want to figure out a variational formulation, weak form, of the PDE we're considering. Okay, so remember, here's the PDE we're considering. It's derivative of x, p of xy, du dx, dy, q, du dy, plus ru f. Okay? And here are the boundary conditions. I'm mostly going to focus just on this, just the PDE. In other words, inside that volume, how do I parameterize the PDE? The boundary conditions follow in a similar fashion through. Okay, so I'm going to define this integrand here, IU, which is given by this here. So 1/2 integrate over the domain. So I had volume and surface, but now this is a 2D problem. So this is inside the 2D domain, and that's on the boundary of that domain. And here is this integrand that we want to look at here. It's p of xy, which is the p of x I had right here, times du dx squared, q du dy squared, minus r u squared 2fu. And then here's the boundary terms on, let's say, just S1. And so the integrand of this thing is given by here. So this is this integral term here. And what I'm going to do now is take the variational derivative of this I here, of this integrand in the domain, so as this means, and I'm going to take the variational derivative of this with respect to u. And what you're going to see, what comes out is, when you minimize that, the result is, in fact, the original PDE. So in other words, I've framed this in its weak form or its integral form by doing so. So here we go. Let's go ahead and do this calculus of variations. So I take that integrand here, take its variational derivative with respect to u, and here's what that formula. This is straight from calculus of variations. Whether or not you had a calculus of variations course, it doesn't matter. I'm just telling you this is a generalization of the derivative, this formula here, and we're going to just plug our I of d into this formula. So we're going to take I of d, take the derivative with respect to u of x. So u of x, u of y, these are independent variables at this point. So when we take the u of x derivative, the u of y derivative with respect to u, this is what we get. we combine terms and shorten it, and this is what you get. In other words, it's the PDE equal to 0. So the variation of this integrand with respect to u gives you back the PDE. So we recovered the PDE as the minimization of this integrand function. And that's exactly what we want to do now. Is that's the weak forms representation of this, which is given by this right here. Now, here is the huge advantage of why you'd want to do this, because this looks like I just made a bunch of things complicated when I didn't need to. But then when I look at this, what's the highest derivative in x? I have a u of x squared, I have a u of y squared. I don't have a second derivative anymore. In other words, I can use my simplex element because the highest derivative here is only 1, which means I don't have to take 2 derivatives, which means I can make use of this very conveniently. Okay, so now, again, coming back to here, I really wanted to use this because it's a very simple representation and a lot less costly than using this or using this. And instead of taking the cost to here, doubling the size of my computations because I have 6 points instead of 3 to get this, I instead rewrote the PDE and kept the cost here and the simplicity here. There's only one derivative needed, and if I take one derivative of this, right, you get one derivative in x, you get b, one derivative in y, you get c. So you get information by taking derivatives versus before, if we took 2 derivatives, I don't have any information to be gained by that. Okay, so now that we have that formulation, now we construct the solution. The solution itself is an expansion in terms of these basis elements, the phi of i's, x, y, gamma I. So in other words, these are all my little finite elements that are around my domain, and the gamma I is sort of the weighting in front of each, so I have to compute all of these and their weights. Okay? And by the way, there's 2 things that are happening here. When I discretize, there's all the interior points, in other words, the ones that don't touch the boundary, don't have to satisfy anything on S1 or S2. Those are here, so there's n elements that don't touch the boundary. And then there are the elements, the finite elements, which is the m plus 1 to the m, all of which touch boundaries. So these have to satisfy the boundary conditions. These are just satisfying the PDE on the interior. Okay? I've already told you this, but all of this is going to lead you to a giant ax equal to b at the end of this thing. Okay? So what we're going to do is take that solution and plug it in now to our integral formulation I of u. Okay? So we just throw in what the solution looks like and expand. Throw everything in, expand in these element bases. So this is my expansion that I have, and I can then start rearranging, and I'm going to differentiate now this solution with, remember before I was differentiating with respect to u, but now I'm going to differentiate with respect to each of the interior points in order to, the parameterization of the inner points, the weights of the inner points, and set it to 0 and minimize this, and that's the computation that's going to give me the solution of my PDE. So if you take the derivative of this with respect to the parameters, look for the minimum. By the way, there is no maximum. There's no maximum error. I can make the biggest error possible. So there is a minimum error, which is if I choose these elements correctly to satisfy this thing being 0. Okay? So here's the partial differentiation you do with respect to this parameter. And now, and again, this is a lot of algebra you have to do here. You're going to collect all your terms, and it's going to just be a giant ax equal to b. Here's what x is. Again, those are all the, and this is just in the interior right now. You have to do this for the boundary terms as well. So for the interior terms, here's what we're trying to solve, right? We're trying to figure out what these weights are. The b are given by these parameters beta, which are given by these integrals here. And the matrix elements A are given by these integrals here. Okay? So once you actually have all this, this is the A x equal to b, and here are the b and the a coefficients. So you have to build A and B in order to get the weights, and once you have those, you can glue all of this together. Okay? So that is the management of all of this that you have to do. Once you commit to finite elements, it is a lot of managerial work. But we've already seen this before. Remember, when we first started talking about discretization, and we started talking about that 2D Poisson equation, we had to start thinking about how do I arrange my data so that when I multiply by matrix, say it's 2 derivatives in x, 2 derivatives in y. Really important that you start to recognize that in most of these PDE systems, a lot of the work is organizational work, arrangement, and you see it here. Now, I'm not going to go through all these details because they're a pain to work out, and it's a lot of algebra, and it's not helpful necessarily to see it on a YouTube video. You could certainly just work it out yourself, or just understand there was a lot of work, because I have some good news. The good news is, so now the good news. The good news is finite element, this management of constructing all of this, it's a one-time process. Like once you've done it once for generic P and Q and so forth, you could build an algorithm that just takes now any new P and Q. In fact, that's exactly what people have done in the community, is packaged up a bunch of application areas, and they've already coded it up. So the first thing you got to do is generate a mesh. And I'm going back to this picture here of this MCL39, where here's a mesh that you might generate in order to solve for the flow physics over this car. Right? This is the MCL39. It's crushing it this year in Formula One, and so you might want to say, oh, what's going on, what's special about it? You could do some flow simulations of this if you'd like. You can download this. In fact, mesh generation is also just its own commercial enterprise. I'm going to take you to this. If you want to see something really interesting, go to like turbosquid.com. And in turbosquid.com, oh, let me get this airplane going again. Oh, come on, I want you to see this. So there we go. So these are all meshes you can actually just buy or download from this website. So here you have this fighter jet, you have this MCL39. Here is a dragon with completely with a mesh on it. So those, they have almost anything you want. The human body, human anatomy, animals, buildings. You can buy all kinds of generated meshes. So the meshing itself is in fact inside of the domain of a lot of interest for a lot of people, and you can buy a lot of meshes or generate your own through CAD. Okay, but this is an expensive trick right here, but it's something that people have made commercially available to you. So you can do very complex problems either by looking online at what resources you have available for mesh generation, or using something like CAD to generate a mesh for the application you have in mind. Okay? Once you have that mesh, you can import it into a bunch of different types of tools. Some are open source, some are paid tools. I want to highlight both, because depending upon where you sit in industry or if you sit in academics, you might have options around what you might use. So let me start off with ANSYS and COMSOL. ANSYS is probably one of the leaders in finite elements. So the package here is it's a paid package. Both of those are paid packages, but they are commercial grade. They have the mesh generation, physics solvers, all of these things directly embedded inside of their packages. Same thing with COMSOL. COMSOL actually came out of a long time ago out of MATLAB from the PDE toolbox to FemLab and all to COMSOL. So COMSOL also solves a lot of multi-physics systems. That's what they are known for. Multi-physics systems, mesh generation, solving on complex geometries. So these are commercial packages that, depending upon where you work or sit, you might have access to. They have cheaper licenses for academics, and so you could do a lot of design work there as well and simulation work. Phoenix, FireDrake, OpenFOAM, these are all open source packages. OpenFOAM is especially good for fluid dynamics. So if you want to do flow physics, this is probably one of the best packages available. A lot of people have built infrastructure upon OpenFOAM, but it will do mesh generation and solution techniques all built together at once. There's always an overhead of learning to use any of these packages, but that overhead is a lot cheaper than writing your own code. That's for sure. Phoenix and FireDrake are sort of two of the standards for more broad finite element implementations beyond fluids, and so I would always recommend Phoenix or FireDrake also to you as something that you can just pip install, and they have a lot of examples that you can start playing with right away. Again, developing the mesh, imposing complex boundaries, complex domains, multi-physics systems. All of these can handle these kind of these issues. And so what you're doing now is using this entire infrastructure of management that you can see happens with finite elements, which from the mesh generation to building the meshes and coding it to AXEB solvers, it's all done for you in these packages. And so you can concentrate on solving problems versus managing all of the solutions there. So that's where I'm going to end here with finite elements. We're not going to actually write code for this because ultimately that means picking one of these resources to use, and typically people would pick whatever is available to them, or that choice is dictated very much by your application area. But just to say that there's so much infrastructure available for you around finite elements. It is sort of this, commercial solves of PDEs are now very mature in these packages, and mesh generation is also very mature. And you can see this even by going on TurboSquid to see all the kinds of things you can download. And that sort of really finishes off how we would handle finite elements, which is in some sense the commercial leader for solving PDE-based systems. For complex geometries, multi-physics systems, this is what you would use, and then you could use one of these packages to aid in quickly getting solutions out.